All right, in this worked example, we're looking at a ballistic pendulum sort of problem. It says a wooden block moves along a horizontal frictionless surface as shown in figure 2.1. And then what you can sort of read in the figure there, they kind of explain underneath where it's labeled figure 2.1. They give you the mass of the block. They say it's moving to the left with this velocity, 2, steel ball, mass given, fired to the right, so opposite directions. These are vectors, so that's important. The steel ball moving horizontally with a speed of 45 meters per second collides. That word collides you see on the chalkboard today, inelastic collisions, elastic collisions. All right, so we use momentum conservation to study collisions. Remains embedded in it means this is an inelastic collision. So you can see in the green chalk on the chalkboard, that's the relevant equation for that. After the collision, the block and steel ball both have speed v, right? They're one new object. And so when we use momentum conservation to calculate v, we say, well, the initial momentum is equal to the final momentum. But the initial momentum is mass 1 times its initial velocity. In general, the sum of the individual momenta of all the particles or objects is equal to the initial momentum. This is a general form of this equation. We need to make this momentum negative relative to this one because the velocity here is actually negative. So we'll see what that looks like here. So mass 1 and mass 2 are stuck together now. This plus sign comes from this word embedded in it, and we're solving for this speed v. I'm just going to leave it in grams because it's going to cancel anyway. I'm solving for meters per second. On Friday, we talked about how it's just sort of good practice to put everything in the SI units, like we'd want this in kilograms, but for our purposes here, it doesn't really matter. All right, so then we're adding the 85 grams times -2. That negative sign right there is, the difference between the correct answer and what's going to lead most students to a sensible sort of answer, like, oh yeah, we're adding the momenta, but this is negative relative to this. So this system, if we look at like the orange chalk, that is a statement of the law of conservation of momentum. Within a closed system, the total momentum in any direction is constant. Here, we're only worried about the horizontal direction. So it simplifies it that way. There are two-dimensional sort of problems, like, is this the right one here? Look at that one. This is momentum conservation too. This ball crashes into this one and then they both go off in different directions. That's a little bit tougher, right? But it's the same thing. Look, they collide elastically, they tell us here. All right, so that's like a preview of things to come. So here it's more simple. It's just a single, direction. And this closed system has a certain amount of momentum. It's equal to the sum of the individual momenta, but the block is negative relative to the ball. The reason why I chose the block or the 2 meters per second as negative is because there's less momentum there. If you actually do the numbers, I think it's like 180 to 170 or something like that. So there's like an extra 10 units of momentum in the ball than there is in the block. This one's much less inert, but it's a lot faster. This one has more inertia, but it's not going so fast. And remember that momentum is the product of mass and velocity. So it's like, well, which one sort of wins the fight here? The velocity, the faster velocity gives this a little bit more momentum than this more inert, slower thing. And so on the right side of this, we've got 89 grams. And this is why, like when we solve for V, the grams are just going to cancel anyway. We solve for V. And that I think gives you 0.11 when you actually do that. All right, so this gives you a certain amount of momentum. This is, 180, right? Because 90 doubled, 45 times 2 is 90 doubled. So 180, and this is twice 85, so 170. 180, 170, so there's 10. 10 divided by 89. Should be 0.11, right? Am I getting that? Yeah, 0.1123. And the units on the left side of this are gram meters per second. So when we divide by 89 grams, the grams cancels and we're just left with meters per second. So that's why it kind of didn't matter that we left it in grams. Again, it's good practice. You could get the same exact answer by converting everything to kilograms, because then kilograms cancels. As long as you convert everything, you'll get the same velocity. But it's a bit simpler to work with those numbers. The question goes on to ask us to, for the block and ball state, the relative speed of approach before and the relative speed of separation after the collision. Clear off of there. So on the chalkboard, there's some sort of re-emphasis of the relative speed of approach equals the relative speed of separation for a perfectly elastic collision. That is not what we have here. And so we're trying to basically show that the relative speed of approach, like what's not on the chalkboard is how do we calculate relative speed? That's a note that you have to be mindful of. When things travel in opposite directions, which they are before the collision, we add the speeds to calculate relative speed. So the 45 meters per second this way, plus the 2 meters per second this way, that's opposite directions. And so the relative speed is 47. Afterwards, you've got an object that's like this, the block and the ball are sort of one new object going at a speed, 0.11. So it's very slow, but to the right. And that's because this thing won the momentum fight, right? It has more momentum. So it turns the block around and they move off together at 0.11 meters per second. They are together. They are not separate, so the speed of separation is 0. There is no speed of separation. Just one new object moving together. And here we can say, well, it's inelastic because the relative speed of approach does not equal the relative speed of separation, right? Just kind of use that language right there. Oh, if you needed a hard copy of this, my apologies. There's some right here. So if you weren't here on Friday and you're like, oh, thanks for telling us now, right over here on the we went over this question that we're doing right now, but I forgot to tell everybody, hey, if you want a hard copy, come and collect one. So don't worry, because this is all on YouTube, so you guys can just queue it up once I'm done. Go back over that first one again if you needed it. If you were frantically copying notes down in your journal, you could, that's good. You got it 2 places, just transcribe it over. Well done. All right, so once again, I think this is question 2, because this is the same question paper that we did the other problem study on with power, right? Like you're taking this paper, you go, oh, define power. Oh yeah, remember this one, the aircraft climate? That was the 3rd question from this paper this year. So the 2nd question was this one. All right, so 47 is not 0. So we say the collision is inelastic because the relative speed of approach, which is 47 meters per second, does not equal the relative speed of separation, which is 0. 47 is not 0. If that was a perfectly bouncy ball instead of a steel ball, and it bounced off of the block and they left each other at 47 meters per second, then those would be equal. And then we'd say it's perfectly elastic. Because it embedded itself in it, the relative speed of separation is 0. And we can use the idea that we derived last week that, hey, because kinetic energy by definition is conserved in a perfectly elastic collision, there's a consequence of that, which says the relative speed of approach will equal the relative speed of separation for perfectly elastic collisions. We'll see a lot of examples of where this, shows up in like paper 1 questions, where you just have to be able to keep in mind that idea of opposite directions add speeds to get relative speed, same direction subtract. That's a really important idea. Any questions on part B2? And then it says, use Newton's 3rd law to explain the relationship between the rate of change of momentum of the ball and the rate of change of momentum of the block during the collision. So the rate of change of momentum is force. Newton's 3rd law tells us something about forces. It says forces are equal and opposite, right? They exist in pairs, equal in magnitude, opposite in direction. So what we're going to say here is that the rate of change of momentum of the ball, the rate of change of momentum of the ball is force, right? So that's the force of the ball on the block, and it's equal and opposite to the force of the block on the ball. There's 2 objects that exist in, a force pair. There's always 2 objects interacting. It's obvious what they are in this example, the block and the ball. And the forces they exert on each other are equal and opposite. That's Newton's 3rd law. Newton's 2nd law really tells us that force is the rate of change of momentum. So the way they've worded it, they've kind of put together the 2nd and the 3rd law. The rate of change of momentum of the ball is force. and it is equal and opposite the rate of change of momentum, opposite to the rate of change of momentum of the block, right? Then we've kind of used the language of the question again. So the rate of change of momentum of the ball and the rate of change of momentum of the block are their forces. And Newton's third law says forces exist in pairs, equal in magnitude, opposite in direction. That's another good way to word it. I just said right now. Pause the video, rewind it a bit, and listen to it again. Right? Or you can use the language that's up there on the screen. It's always good to sort of think about it yourself. It's like, oh, how would I state this? I'm kind of putting in my own words here. But that gets the key idea. All right, this has been another worked example with Dr. Schleif, and we'll see you next time. Or probably this one.